So we have an element G in Sn, and say there's sort of a natural action, of Sn, where this field will just get transformed into the map of the ith copy into the Gith copy, and this can be generalized for more complicated fields, which could be products also. But then in the symmetric, with the action of G, we can also then introduce twist fields. Sigma G, and here at this point the sigma G is labeled, by an element of Sn, and these introduce basically a non-trivial monodromy of, say, my fundamental fields. So if I take phi I around the twist field, it gets mapped not to itself, but by the action of this element G. Okay, and please interrupt for questions. So at this point we haven't orbifolded yet. Yeah, and so obviously, as I said, there's, I guess we've even talked about it in the lecture. There is sort of a way of phrasing all of this in the language of categorical theory and generalized symmetries, the gauging or condensation or so. Here I'll be old-fashioned. So the first step in the Sn, so that's synonymous with the symmetric orbifold. The Sn orbifold is to project onto the states which are in the tensor product into Sn invariant states. And so, say the simplest one would be that I'll basically say, if I have a field phi in the copy I can just take the sum. This is clearly invariant, but then one can again generalize this to more complicated fields. Something also happens to the twist fields. Yeah, obviously a choice of G would not be Sn invariant. So what happens is that in the orbifolding, a twist field would get conjugated by elements of Sn, and that means that the elements in the in the twisted sector, and we'll talk about how this comes about with modular invariance in a second, would be labeled not by elements of Sn, but by conjugacy classes. Yeah, so basically, this would be something like, say, I have L11 cycles, L12 cycles, say, and Ln cycles. Obviously, they cannot all be, non-zero generally, but then I have this partition of N. Okay, and so one way to understand, even the necessity of, that I have to introduce these twisted sectors is modular invariance. So when I start with the partition function of the seed theory, say trace of, so this would be the partition function of the tensor product, I'm sorry. So this would be the C of the full thing. Where L0 is basically the sum, of the zero modes of the 0-0 algebra, summed up. And Q is sort of the standard modular parameter on the torus. Sort of one way also to write this would be that, I just write sort of a square torus and put sort of 1 here, and hopefully the notation will become clear. So, this is not neither projected into the into Sn invariant states. So if I insert a projector, what I would do is I would basically put in, so say, the first step would be the projection. I put in the sum over the action of all the Sn. So this would be a projector onto Sn invariant states. And here in this notation, I can basically put in a G, I don't know what G, and then I basically put this in here, denoting the action, and that is actually, I guess, like what Sora said in his class. This you can think of as like an operator acting, on the Hilbert space on the torus. So this partition function is not modular invariant, but we can make it modular invariant. And for example, you see that what happens is if I make a modular transformation, say, which exchanges tau to -1 over tau, yeah, what would happen is that I would actually exchange the A and B cycles on the torus. So clearly there would be, in this notation, a sort of 1G. What is that? That would be a sector which is twisted by G. So, again, this is just review. So to make a long story short, basically the partition function of the orbifold theory can then be viewed as follows, that we we'll insert these projections, both in the space and the time direction, and we interpret these as the as belonging to the twisted sector. This condition, that these are a commute, has to do, with the fact that I can kind of undo the things which do not commute on the torus. Okay, sort of, this hopefully. Okay. So there is also, so this is really like kind of, going back to the mid 80s or so. This kind of language. There are sort of two other ways of writing this this partition function. Which are instructive. Again, I won't derive them. The main idea here, actually, in doing this, is not to take a fixed n, but look at a kind of grand canonical ensemble, which basically gives you the partition function for all n. Introduce sort of a chemical potential. So we would have another parameter rho. For us, this doesn't really matter so much. We can basically use it to read off like a specific value. And then there would be basically this partition function. So the two ways I want to write this, and this, again, is, I think I'm not, if you haven't seen this, I'm not sure how much this will really help, but I think I wanted to sort of illustrate a point. So this is sort of the first one, which I think, I'm not exactly sure. Goes back maybe to the work of Van Tai, or so. But what is this TL? This is a Hecke operator, and so again, the details don't matter. They matter obviously to make this correct, but sort of one thing I mean the way so this looks kind of incredibly quite complicated, but basically one way of thinking about this action of the Hacker operator is that it sort of defines in a sense a way of understanding the different contributions to the partition function as a covering map, yeah, of basically a torus with a different modular parameter onto the and where basically say multiply cover the original torus of the C partition function.
Sorry.
Yeah.
The summation in the second line is.
Oh yeah, I think. Sorry.
No, above the second line.
Yeah.
A. From minus.
One. Oh, so yeah. So AD goes from 1 to L, and then let me see. I think A divides D, or actually. Oops. Okay. So much. I mean, so I guess there's probably a bigger expert in the audience about Hacker operators.
No, just a stupid question like L, is it from minus infinity to plus infinity, excluding
A
zero?
times D is equal to, yeah, sorry. Well, I mean, so, yes, yeah, I mean, so L is, oh, sorry, from 0 to infinity, yeah.
Well, but you divide by L now. You're from 1 to infinity.
Oh, yeah.
From 1 to
Well, I mean, I guess there should be probably still a 1, but that doesn't really make it, no, there shouldn't be a L equals 1.
and you divide by L, right?
Yeah. But I think the main point, I mean, what this formula says is basically that you have this idea of looking at the symmetric orbifold basically as that there are sort of two spaces. There's the space where, I mean, say, the conformal field theory is defined, I mean, the original symmetric orbifold, and then there's a covering space. So this needs to illustrate like some, I mean, this idea is also present in the calculation of correlation functions. And this goes back, and this in the physics literature, we had to, I mean, work by Lunin and Montour, and then Rastelli, Razamat, and Pacman, etc. And so.
Say again what Sept is?
Oh, this is, sorry. So this is just, sorry, this is tau. I mean, sorry, there are too many taus. Yeah. So this would be actually basically that, okay, let me not call it tau, let me call it Sept. Yeah, it's the.
Yeah. I see, that's the original CFT.
Yeah, exactly.
And then you're applying this. So you could take that, if you feel like it, you could take it out of the exponential.
Well, I mean, it's acted on, and then you expand it, and then you basically pick out the power of rho to the n to get the second orbifold. So this idea of a covering space, basically, like what you can look at is basically a partition function of twisted sector fields, and here I should say here this is basically in some sense say the simplest case where I mean these could be viewed as twisted sector ground states. I mean, meaning that the only thing they do is impose the holonomy. I mean, there could be also basically an operator from the Sept theory also localized there. But I mean, the simplest case would be this. And what basically these Luni Matura and Ostelli et al. Found is that you can kind of analyze this, this correlation function and then basically have sort of a diagrammatic extension which leads to basically a correlation function if these are just twisted sector operators on basically covering Riemann surface, where basically the fields are single valued, and one could say for in this case one could just evaluate every single contribution by just evaluating basically the vacuum correlation function on this on this covering Riemann surface. So what comes out of that, yeah, is basically the behavior of these correlation functions, which sort of goes towards, as I said, a behavior which is reminiscent of the behavior of holographic theories in the large N. So, namely, that there is this is obviously not deriving anything, it's just a statement of facts that in a large N limit, there are dominant contributions. So what you really would have to do, you would have to actually write this, basically these correlation functions, say, as, again, these conjugated individual twist operators, and then fuse them together. That will be the covering surfaces, and then evaluate everything. It's technically complicated, but what comes out of it is that that there are basically there is the so-called single cycle twist fields. That means that this conjugacy class is really just a single a single ZL cycle or so, and not made out of many cycles. In some sense, dominates and displays a large in factorization. So that means that, for example, that if I look at the correlation function in the there is sort of a universality. That means that for the dominant contributions, the details of the seed CFT really don't matter, other than the central charge, which is basically just scaling with n. And you can kind of, see that here, that for these twist operators, you basically map them into a Riemann surface without any operator insertion. So the details of the seed. And then that basically these that the dominant contribution of this to this is basically the sort of the 2-point functions of like two contractions of two cycles. And what that means is, I'll talk a little bit, that's, I think, all I want, I guess there's one more thing about this CFTs, but we maybe can remember that that these are maybe properties which you've seen sort of if you, I mean, in holography or ADS-CFT duality. For example, that basically this, especially this statement, then if you compare it, say, to the canonical example of say, ADS5, type 2B ADS5 times S5 to n equals 4 super young mills, or generically like gauge gravity duality, that these single cycle twisted sectors are sort of like, I mean, we could say generalized free fields or single trace states, and it could be sort of identified with sort of single particle states in the duality. Okay, so maybe the last thing, I mean, that these formulas, and I mean, there's another one which I don't write down due to a digraph Moore for Linde and for Linde. I mean, basically, and generically, that I mean, the modular properties allow you to look at the at sort of the growth of states, yeah, at large n. Large n, and in some sense, basically, what happens. This goes back to work by from Keller and Hartmann. I mean that there is also a sort of a universality that so that the contribution, say, of the free energy. I mean, I'll sort of write this a little. Where this, I mean, would be, say, if I think about this as a thermal partition function, yeah, and this would be the temperature and the, I mean, the inverse temperature, 4 pi squared over beta. But the main thing here is that basically the growth, and then sort of plus order 1, and things falling off, that again there is a universality, that it only depends, I mean, the only thing that comes in is the seed center charge, not the details of the CFT, and maybe, I mean, again, that there is in some sense the spectrum is sparse. I mean, that I don't really want to write a definition, but basically that you could imagine that if you look at states with relatively, I mean, small conformal dimension, that those in the large n limit would just grow without bounds, and that doesn't happen. So these are all the kind of properties of symmetric orbifolds. Yeah.
Can you repeat the universality? No seed. What doesn't depend on the seed CFT?
Well, I mean the form of the form of the correlation functions in the large n.
By form you mean just the functional dependence,
yeah,
like the actual function.
Right.
Okay. What if I start with a two-dimensional topological field theory as my seed?
I mean, well, I mean that's not. I mean, I would say a topological field theory is not really a CFT.
Okay.
CFT. I mean, they're not really any local.
At least the easing CFT or something on trivial.
Yes. But I mean, you would have. I mean, basically, the point is, I mean, you take a seed CFT, but then you really take the large n limit. I mean, so it will always be a CFT with, I mean, a very large central charge.
Okay.
But if you take a supersymmetric seed CFT, then there might be, for example, a topological subsector or something.
Okay.
Correlation functions.
Yeah, I mean, I will actually talk a little bit about supersymmetric seed theory, and then we can come. Okay. So now I'll.
So when you say topological field theory is not a CFT, does that mean you assuming that your CFT has a unique ground state?
Yeah, I mean here basically again, I mean I mean what I'm looking basically at the end here is, I mean in the examples I work with would be what you would call like I mean unitary compact CFTs. Yeah, so unique ground state.
Because then clearly you talk about the correlation functions clear in what vacuum it is calculated. So if you
Yeah,
have
these
some-
would be,
yeah,
yeah.
if you say you have many of them, so you have many different limits for them. And he's drawn a correlation function.
Yeah, I mean,
in what vacuum?
right. I mean, I could, for example, I guess there are other limits. I mean, I think what I'm sort of doing here is that I kind of fix the twist or the length of the say the single cycle, and I wouldn't take that one to infinity at the same time. I mean, there could be probably some kind of other double scaling limits, or so you could think about that.
So you presented it as if you can do it for any CFT. Is that really true?
I mean, what do you think?
Like for instance, if you try to do a Z to orbifold in some theories like chiral fermion, you cannot.
Oh, okay, yeah, okay. I guess all the examples I'm thinking about here would actually be, diagonal partition functions. Yeah. So you would say if this theory actually has an anomaly, then you can.
Not the theory, the n copies.
Okay.
You're gauging the SN in the n copies theory.
Right. So, but with the so would that theory be considered in the original? Okay, yeah, I'm not sure.
Take one by one.
I think there's a,
Say again?
I thought there was some kind of theorem about like this kind of SN symmetry and permutational orbifold being anomaly free. No? I think it's like a mathematical theorem. Yeah. Canon, yeah.
What did they do? What is it? Another?
Yeah, if you take an SN action like this, it's not anomalous.
Okay. Well, I learned something today. Okay, so I wanted to just briefly say just a tiny little bit about ADS 3 CFT2. And again, this is very idealistic and sort of review.
Let me just ask a random question. So you introduced these Hackett operators. Is there any relation at all with Jeff Harvey's work on Galois theory in CFT?
I think you're asking the wrong person. I don't know. I mean, I guess they appear in all sorts of like number theoretical, algebraic, like number theory situations. I mean, I think in the orbifolds, it's really sort of a very. I mean, I think this goes. I think that's also mathematical work, but basically this idea of like these covering spaces, but I'm not sure. I mean, actually, I'm not familiar with Jeff's work.
Can I ask some basic to catch up? The D there is for some fixed A, you have your orbital partition.
Yeah.
And then what's beta and beta prime?
Well, so this would be basically. I mean, I think about the torus partition function basically as a thermal partition function, and then I can either look at the limit, say, of large temperature or small temperature.
So beta is the inverse temperature.
Yeah.
And what is the beta prime?
So well, that's the 4 pi over beta.
Oh.
Okay, so I mean, so basically the one fact about ADS3, which actually predates ADS CFT, is the result, I guess, to Brown and Haneur, that the asymptotic. I mean, if you just think about gravity in ADS3, that you can think of basically the asymptotic symmetries. I mean, due to the kind of diffeomorphisms which end up not being trivial on the boundary, they satisfy the Virasoro algebra, and and there is a central term which has the radius of ADS over the 3-dimensional Newton constant. So, I mean, this kind of, and this result is, yeah, I mean, as I said, I mean, was known in the, I guess, was it late 80s or so? I don't know. Anyway, I mean, predates ADS CFT. And so, what you can kind of learn about that, if you want to look at in say an ADS 3, or like, I mean, maybe in a more top-down approach, having, say, a 10-dimensional spacetime which has an ADS 3 factor, that if you want to look at a kind of description of semi-classical gravity, you would, so basically you ask the question, I mean, what is sort of a CFT2 dual? That, for example, we need then that the curvature radius of the ADS space is large, so this means that we should have large central charge. And that's already one indication that these symmetric orbifolds might be useful. Yeah, that is a way of constructing CFTs with a large central charge in the limit. And then there are then basically also arguments for this. I mean, this sparseness. I mean, has to do with the fact that, say, if I construct such a gravity theory, I mean, if I just have gravity, I basically don't really have any no matter. I mean, that's still, I mean, maybe a little tricky, but I mean, in any sort of like supergravity solution, I would have, say, a number of massless, I mean, supergravity field, or and then I would have string states, but say if I mean, LADS is large, they would be very massive, and the mass, I mean, in the basically of excitations in the ADS space should be related to the scaling dimension of operators on in the dual CFT. So you would expect again that there are not that many operators of a small scaling dimension, and then that, say, the calculation of correlation functions, I mean, would happen due to, say, I mean, calculating Witten diagrams, I mean, using the semi-classical action, and that would mean that interactions, I mean, where I'm not just contracting, say, 2 points on the boundary, would be suppressed, I mean, by powers of the coupling constant, and that would basically introduce sort of the notion of factorization. So, I mean, all of these, yeah, are basically, I mean, that's the good news. I mean, there's also bad news coming later. Points that maybe symmetric orbifolds are actually useful in the, I mean, in ADS3 CFT2 duality. So again, because I think it's, I mean, an audience just of string theorists, I should just sort of make a couple of comments how these orbifolds come about. I mean, historically, the first, I mean, there is actually a realization of the symmetric orbifold. I mean, the history is a little roundabout, but I mean, you remember that the basic idea, I mean, of holography is that I have, say, a bunch of D branes. Say, I mean, the canonical example, I mean, would be D3 branes. I bring them close together, and I take a decoupling limit. I mean, which means, say, if I look at the open strings, sort of a low energy limit, which means that I get for D3 branes, say, super Young-Mills theory. I mean, n equals 4 super Young-Mills, and then in the geometry, I take a decoupling limit which is sort of going to the near horizon regime of the back-reacted gravitational theory, and that, say, gives me in this case ADS 5 cross S5. I mean, that's sort of the canonical example. But basically, almost at the same time, or I guess it was even, I think, in one's original paper, there is also basically the situation where I take, say, N5 D5 branes and N1 D1 branes, and then if I write here the 10 space-time dimensions, and I wrote them so, and the way I set this up here is that I'm not taking 10 flat dimensions, but say I have these 4 dimensions, which could be which are, say, compactified on the T4. I mean, and so basically the D1 brane would be on the in the 0, 1 direction, and the D5 branes are basically, I mean, share these directions, and wrap the T4, and so I guess okay, I guess I should. But basically, what happens is that you can basically do exactly the same analysis of finding a low energy limit of this brane system. I mean, now it's more complicated. You know, there are strings going from the D5 branes to the D5 branes, from the D1 branes to the D5 branes, and from the D1 branes to the D1 branes. But basically, the outcome is that on the gravity, we get basically a space-time alias 3 times S3 times T4, and one way to describe the low energy system, yeah, on the branes would be like an n equals 4 superconformal field theory. And basically, I mean, you can think of it like a sigma model, and then that the target space of the sigma model is basically the space of sort of n1 instantons in the UN5 gauge theory. I mean, this is just in effect, and then this modular space would basically be associated with a T4. I mean, this is actually not exactly the same T4, but then a T4 to the n is an orbifold where n here is basically n1 times n5. But what was realized, I mean, at this point is that this theory has I mean, it's not exactly at the orbifold point. And what that means is that it is basically deformed away from the orbifold point. Because, I mean, basically, and that's sort of the last part of my resolution, that I said there are, like, in the symmetric orbifold, it displays a lot of the properties which you would want from a I mean, holographic dual, but it also, I mean, if I am at the symmetric orbifold point, it also has properties which are not, you know, which you wouldn't expect in in sort of a in a supergravity dual, and that is, I mean, that if you look actually in more detail at the growth of the partition function, what it displays at the orbifold point is sort of a Hagedorn growth. Which means that it's really stringy. And the other thing is, at the symmetric orbifold point, you also can construct many additional conserved currents and even higher spin conserved currents. And then I think recently things like, say, for example, that you look at out of time ordered correlators. I mean, thermal correlators, that they don't display, say, chaotic behavior, etc. So the notion is then that basically, if I go, I mean, if I'm actually looking at I mean, so maybe for a general as an orbifold, to go to a semi-classical gravity, I would have to basically, you know, deform away from the orbifold. Okay. All right. So now we're coming to topological defect lines. So we'll forget about the CFT.
Can you move up this other board?
Oh yeah, sorry. It's not quite elastic scattering. Okay, so basically the way I mean, I wanted to just remind you about quite a simple construction. I mean, because we'll actually also use it of say the Verlinde lines in say in just say rational conformal field theories, and this goes back to Petkova and Super. I mean, here I'm thinking about the sort of say the simplicity and diagonal partition function that so in this case, I mean the topological defect lines are labeled basically by the same label as the primaries, and I can use the modular matrices to basically create, I mean, write this topological line basically as a projector, and then it basically it's I mean sort of like say this projector sort of can be written using this, I mean, basically the analog of Ishibashi states. Yeah, so this would be the left and the right, and then basically I mean, what basically cause, I mean, these are basically sum over, I mean, all descendants, the same kind of argument which was used for the Ishibashi states, say in conformal theory, can then be shown that this, indeed, this line operator is topological. I mean, it commutes with all the 0, 0 generators, and then again, I'm just recording this, that basically the fusion, then the fusion product of these is simply given by the, I mean, by these integers, I mean, which can be expressed, I mean, via the Verlinde formula, and it's basically the same, which appear in the fusion product of the primaries. I mean, one thing we're sort of using, and I guess it might not be that super familiar to, I mean, everybody is using the folding trick. And so what we do there is we're basically, I mean, this is maybe more familiar in the case of the say of a conformal defect, but I mean it's maybe a little bit instructive to see what happens if you do the folding trick for sort of this topological line. So I mean what this means is that we take say the CFT. I mean here 1 and 2 basically means, I mean, to the right and the left of the line, and then we fold say the second CFT over, and we get a boundary state, and so and so I write this. So the boundary state then basically changes what is holomorphic and anti-holomorphic for the second CFT. And here, I mean, we're summing over. I mean, this is the label of the primary, and then but here there is a sum over the over all the descendants. I mean, sort of in the Ishibashi state fashion. Yeah, and but I mean these two are independent, and so if you sort of look at these boundary states, you actually see that this is kind of like a permutation brain. I mean, I guess which was introduced by Watts Yeah, rectangle, exactly. So that that basically, if you were to, for example, if you would write 1 here and 2 here, what this would be basically a complete, would be the tensor product of 2 boundary states, and would be sort of a completely separate, separating defect. But basically, I can do this, and then I can permute the CFT and get basically a boundary state which would be basically the folded topological line. In this construction we kind of use, and so the commutation of Ln basically then means that here we have so the that the that if it were completely separated, then I would have a 1 here and a 2 here. So that that this would be a boundary state of CFT1 and CFT2, but then here 1 and 2 are exchanged, and then if you unfold, this exactly becomes the condition for that the associated defect is topological. And basically, in using this kind of boundary state formalism, what one can basically calculate the quantum dimension of the line, simply by acting, say, with the vacuum.
Your notation, the sum over n is the left moving modes and n is the right moving modes.
No. Here basically, like, in the Ishibashi construction, I'm basically summing. This label labels all the would basically be an Ishibashi state. Where I have, say, the descent. Say sum over all the descendants of Ln. But then basically, at the same time, basically, it's basically in these 2 states, it's actually the same n. But this is then with basically created with L minus 2 and I or so.
And the subscripts 1 and 2?
Basically denote the 2 CFTs, basically left and right. Or after folded, it would be the 2 factors in the tensor product. So basically this would be then the quantum dimension. And then basically, like, because then you would just pick out the vacuum, which would say be I equals 0 here or so, but then I would basically get the, and this would be analog of, like, basically, shrinking, the line to 0. One can also do more, so basically say if I wanted to act with a primary state on this boundary state, then again, because this is sort of constructed as sort of a diagonal sum of the primaries, you would basically get the action of the line on an operator, which this is not really like super canonical notation. But basically, this would be the having a line around a particle, an local operator, and shrinking it to 0, and then here we would have basically sort of phi 2. So, and for example, like if you do this with this, you get indeed, like say for the minimal models, you get that the quantum dimension of the line, say LA would be SA0, S00, and so on. Okay, so now I wanted to basically apply this, sort of more pedestrian way of constructing topological defect lines to the symmetric orbifold. And so basically we look at two classes of topological defect lines. I mean, one would be basically the universal defects. And then obviously, I guess we look at non-universal defects. So the universal defects are the ones, I mean, you know, like in this maybe more fancy language of basically gauging Sn. I mean, that then there would be, I mean, lines which are elements of Sn, and then you gauge them, and there's basically a dual quantum symmetry, which would be the topological defects lines in the orbifold theory. And then basically these would be labeled by rep Sn. And I think we discussed this maybe in at least a little bit in the, I think in some lecture last week. So what I mean with that is that these lines are labeled, I mean, by the representations of the symmetric group. And I think this is probably more general and could also be applied to permutation orbifolds, etc. But I'm just doing that. And so this means that, again, these are sort of universal, I mean, in the sense that they do not depend, I mean, on the no dependence on the CFT. The non-universal defects, basically, I mean, the ones we're constructing, and I don't think we may claim that we've really found all of them, I mean, that will basically combine, I mean, the action of the symmetric group with basically the, so plus, I mean, it's not exactly, it will not be a rep Sn, but basically that we'll take the topological defect lines which are already in the Sept theory and basically use them and combine them and with the action, I mean, of, with the symmetric group to construct more topological defect lines. And those then obviously will depend on them. And in the main, like, I mean, maybe to go to sort of, I guess, since I'm actually really running pretty slow, 1 minute. I guess, I mean, I can go a bit longer than 1 hour. Is that,
Well, it's an hour and a half. Yeah, you can run over.
okay.
It says an hour and a half in the schedule.
Yeah, I guess I was sort of an hour plus half an hour per
half
question.
an hour of discussion, but please go.
Okay. Saved by the bell. So I guess I'll run out now, or in Schwinger fashion. So, well, he used to do that. I think I've been told. I wasn't there in UCLA when he was still there. But that he would basically finish his lecture at the right board, and then he would just at the exact second when the class finished, and then he would walk out of the room. So basically the idea is here that, I mean, we'll construct these universal defects, and then we're basically looking at at the question of which of these can be preserved if I do a marginal deformation in the twisted sector. And I mean, the reason why, basically, if I do a marginal deformation sort of in the Sept theory, I would basically deform the kind of Sept CFT. I mean, that could also be interesting, but that's not what I'm after. Because I wanted to look basically at going away from the, I mean, the question is, if I can make a deformation away from the orbifold point, it can take my theory closer to basically being described, say, with the semi-classical gravity theory. And then basically the question is, do any of these topological defect lines survive? And I mean, one thing I mean, will show is that there's basically very little survive, but definitely none of the universal defects survive. So that's why we're also looking at some of the
Survive under the formation of the orbifold.
Yeah. Yeah, so basically we look at say at a marginal, exactly marginal deformation of the Sept theory. In the twisted sector of the orbifold. So the examples, I mean, we work out are basically the ones where we use n equals 2 minimal models as the Sept theory, because there we can, with like Susanne Bintani actually in Berlin and company, they kind of classified basically all the marginal.
Does the ADS dual have SN gauge fields? maybe it's good that you broke them because maybe there are.
Yeah, no, I don't. Well, we don't know what the ADS tool is for the minimal models, but
No, I'm saying
yeah.
even for the constructions of the
Yeah.
D1 system.
Yeah, no, I don't think. I mean,
So
no,
if there was a
yeah.
represent on the boundary, there would be some SN gauge.
Right, no, exactly. Yeah, I mean, it kind of
And
makes
that
sense.
doesn't make sense.
Yeah, exactly. I mean, I think that is broken is a good thing.
It's a good thing.
Yeah, but I mean, on the other hand, maybe, I mean, originally we were maybe, I mean, it would be interesting to see then to either, you know, that if you could disallow, I mean, or like that some say I mean, it's still very challenging to interpret non-invertible symmetry, say, in a semi-classical gravity theory. So that this might be an indication of what theories might have, you know, like a semi-classical do it or not. I think that the outcome is actually that no non-invertible symmetry, I mean, maybe that's the punchline, that what we find in these classes of our defects, I mean, we look at that no, I mean, we kind of prove a theorem that basically no non-invertible symmetries survive.
But they do survive as conformal defects, probably.
Yes.
So not as topological.
No, that's right. I mean, you would expect that if you make a general marginal deformation,
Yes.
that topological defects would turn into conformal defects. Yes.
Yes, but then they would still have some holographic.
Yeah, but then you might say, okay, these then could, well, I mean, then I don't think they're kind of, I mean, there's still fusion, but it doesn't become, it's not like a topological
Yeah.
fusion anymore. You have these divergences, and you could maybe entertain that they might become just like, kind of like brains or something like that. I mean, brain-like defects. But okay, so, I guess I have to speed up, but basically maybe I'll leave out some of the details, but this kind of Petko-Azabir or the, you know, this folded boundary state description can kind of be nicely used to describe, I mean, to construct the defects. So maybe I'll leave out the boundary state. So basically here, what we'll do is we'll basically sum over all the twisted sectors. So the line is labeled by the representation. Yeah, so what comes in is the character of the representation, and then basically a projector. Yeah, and again, this would be can be kind of constructed in this Ishibashi-like state in the G twisted sector for left and right. And for example, what you can show, I mean, using the character orthogonality and the kind of you know, Kronecker product, that the fusion of these indeed basically follows the representation theory of Sn. Yeah, so I mean, up and down doesn't really matter because these representations are real. And that the quantum dimension, so I mean, basically say the quantum dimension of these lines would just be I mean, you basically, if you think about it, like, again, I won't write it down because, I mean, for time, but if you were to say unfold and then look at basically, I mean, use this formula with the vacuum, I mean, basically the vacuum is in the identity sector. So we evaluate the character at the identity, yeah, which is, I mean, the identity conjugacy class. So this is just the dimension of the representation, and then so basically and again, this is it's not the greatest notation. I mean, what I mean with this, I mean, it would be when I use the folded the folded construction. Yeah, basically I act with say a state on the a primary state, but then a state in the twisted sector, yeah, on the boundary state, and that will give me basically the action of the line operator on this local operator. And that basically here turns out to be then basically just a character of the say of the of the conjugacy class G. Yeah, and so maybe what I'll actually do in the interest of
Wait, it has to multiply phi, no? It's an actual operator. It cannot just be a number. It has to be a new operator.
yeah. Sorry, I mean, I guess, well, I mean, well, basically, yes, I mean, well, I mean, it's the action, and then it's basically the prefactor. So if I do it with the line, I mean, I would basically, so then, I mean, if I enclose it, I would basically call the,
Okay, so this is the prefactor.
yeah,
around it.
yeah. And so maybe, I mean, we do this also for this, I mean, for this non-universal defects, but maybe let me first, like, kind of give the, I mean, the argument, which is almost, I mean, quite trivial, for this universal sector, and then we'll see the organizers give me a little bit more time to, I mean, at least sketch the non-universal case, and then, so basically, what we want to look at, I mean, is that if we were to deform as our symmetric orbifold CFT, say by a exactly marginal operator, and I mean there are obviously conditions on that. I mean that basically the examples, I mean, which are easily manageable, would be things where, say, this would be like a current deformation, yeah, but that's not really that interesting for us, because that would not really be, say, I mean, generically in the twisted sector. Or what we're basically looking at is that we look at the n=2 minimal models, yeah, where, I mean, you're guaranteed to have descendants, I mean, say, of a dimension 1/2 primary. I mean, super descendants are guaranteed to be exactly marginal. But even in some sense more general, right, if we assume that we have here a field, I mean, which corresponds to an exactly marginal deformation, which would be, say, in a twisted sector, so basically the question is, under this deformation, yeah, will the topological line remain topological? And I think this was already discussed, I mean, by Chang and et al., or like Zi's group. And basically what we're looking at, say at topological defect 9 lambda, is preserved, yeah, under deformation by phi, yeah, if basically lambda and phi commute. And I mean, what does that mean? Yeah, I mean that means that I mean basically if I take, say, the line through the operator, that there won't be basically a lasso edge. Yeah, in general, you would have something, you know, then I mean, a little bit, realistic. We would have basically a non-zero, lasso action. So basically this should be 0, and that can be translated basically that if I look at, I mean, this action, yeah, of the line on phi, that this should basically be equal to the quantum dimension on phi. And I think then basically for, I mean, I think the proof, like you make certain assumptions, I mean, but definitely for, I mean, for unitary and compact CFTs, that basically implies that, I mean, this non-trivial lasso action has to be 0. And so for us, I mean, basically, we calculate, I mean, this action, yeah, I mean, we know that, say, the action of lambda on phi, I mean, in our funny notation, would be this, yeah, and therefore, basically, the condition, I mean, is simply, say, if I take the ratio of the action of lambda over the quantum dimension, that should be 1. Yeah. And so, for example, yeah, I mean, for our unit, so that already basically tells us that in the case of the universal defects, I mean, this is not possible. Yeah, simply because this ratio, yeah, so say if I take lambda r, say, and the phi in the G-twisted sector over the quantum dimension, so basically what we will get is that the character of the representation in the conjugacy class and or the character in the identity or the dimension, but then basically that I mean, I guess that's a theorem in representation theory of Sn, that basically the dimension, I mean, of the representation is always larger than the character, I mean, in a given conjugacy class. That, I mean, that is, so basically only, yeah, if G here would be 1, yeah, then, I mean, this would obviously be trivially 1, but that would be basically a deformation in the untwisted sector. You could also argue that here, I mean, there's sort of two more things. So basically G.
What about like the sign run?
Yeah. So okay, I'm coming to that. I mean, there's two caveats here. So G is identity. I mean, that is preserved, but that's basically, I mean, for the universal defect, that's basically nothing. Yeah. I mean, that's the trivial defect. So that's not really a surprise that it is preserved. Yeah. So I mean, for the alternating, well, I mean, then the character is actually -1. So what this means is that the line would actually anti-commute. So,
but not for all G, right?
No, what? No, here. I mean, this is the conjugacy class. So, well, yeah. Sorry.
Yeah.
No, that's right. I mean, so we would. Sorry. Sorry. That's right. I mean, for even G, it would commute. For odd G, it would anti-commute. So indeed, I mean, actually, there is basically the alternating representation. Yeah, with even G is preserved, but those are invertible. I mean, so basically, these would be cases where and then alternating. So for G even, we would actually have lines which are preserved. But they're inverted. And there is one more sort of sporadic example, and that is n equals 4, basically with the 2-2 representation. That actually has basically, there's one example where we would take the representations and I mean the conjugacy classes are labeled. I mean, the representations and the conjugacy classes are sort of labeled by partitions of n. And then basically, I mean, this example would actually be this is basically sort of the only non-invertible example in the end.
this example is preserved.
Yeah, this would be preserved, but only for n equals 4. I mean, so it's not really that interesting in large n. I mean, it's sort of like one exception.
Oh, sorry, n equals 4, like this n, not like
S
n
n.
equals 4 supersymmetry. I see.
No, yeah. So, okay, so
You use some, yeah, sorry, just, I don't remember that, but yeah, I guess if the ratio L5 to L is 1, that's a necessary condition for having no lines. But it's not a sufficient condition. Probably it's not important for you, right?
yeah.
I mean, it could be that the operator goes through and leaves behind some kind of topological line, and still L5 over L is 1. Isn't it possible? I think it's possible.
Well, I mean, I think it depends on the CFT. I think for unitary compact one, I think it's not. I think we'll actually. Okay, I mean, I can maybe show you the. I mean, since the paper is not yet out, I mean,
And do you mean diagonal as well?
yeah, I mean, well, okay, yeah, I mean, for the ones which we actually constructed. Okay, so maybe I mean, without writing the details, I mean, just sort of sketch what kind of non-universal lines we're having, and then basically the upshot is that this argument, this argument about this condition for preservation actually basically holds still. I mean, so that meaning that we find, I mean, again, unless there is some sort of spurious example, say for generic n, that all the non, I mean, even for the non-universal defects, the only ones which can be preserved under twisted sector marginal deformations would be ones which are invertible. So no non-invertible ones survive. And then the example of this sort of n equals 2 minimal models is then just kind of a construction, I mean, saying that that is actually then not that special. I mean, that there are basically for seed theories for all these, at least the diagonal n equals 2, I mean, in the A series, that basically for any of these, I mean, we can find invertible lines which are preserved, which have, say, also the, I mean, generically in the either the identity or the alternating representation. So both basically, they have to be, I mean, basically the red Sn in some sense part has to be invertible, and I mean, furthermore, the actual line, I mean, the seed line also has to be invertible. So that's, and so maybe I'll just look at the, and this is a little bit more. But maybe I just sort of say what we do is like for the non-universal ones, and that sort of, and then I basically just summarize our results. I mean, I leave the the calculation for this. I mean, I really can't do it in finite time. I mean, so for the universal, what do we have? What kind of data do we have? I mean, so we kind of assume that the CFT has sort of a finite number of lines. Yeah, so it would be something like the Linde lines or like basically an RCFT. So the data we have is basically, and this is very similar to the construction of boundary states in symmetric orbifolds, I think, which was done by Bellin and collaborators and by Matthias Gavadil and was it Eberhard or some of his students or something? But anyway, I mean, so basically that we take a set of numbers, I mean, n1 to nr, yeah, and then basically and these sum up to n. So we're basically, in some sense, sort of like an untwisted I mean, our untwisted set is of lines would be that we basically take n1 copies of first line, and then n2 copies of the second line. I mean, we sort of put in some ordering, I mean, which is a little arbitrary, but, and then basically n copies of the last line. And so obviously this choice, I mean, it's not Sn invariant, so this wouldn't, I mean, so basically these universal defects are not labeled by rep Sn, but instead basically, so this would be first thing. The second thing is that then we're basically looking at a stabilizer, and the elements in Sn which leaves this invariant, which would be like Sn1 times Sn2 times Snr, and then basically look at, I mean, instead of a representation of Sn, we're looking basically at representations of Sn1, Sn2, and so we can basically say construct these and evaluate the say the quantum dimension and evaluate the action of local operators on these, and basically the statement here is that then basically this condition, I mean, is in some sense, I mean, in some sense a little bit more stringent. Yeah, that basically what happens is that the only reserved PDLs would be basically the kind of maximally symmetric ones. What that means is that basically we take, say, I mean, I do 1, 2, 3, but basically one of them, say the Ni has to be N, yeah, and therefore basically all the lines, I mean, this is sort of the simplest choice, yeah, that all the lines are the same, but they're not necessarily the trivial line. That would be basically the universal one will say, and then that is still that we have a representation. Yeah? I mean, because then the stabilizer of this is actually the full Sn, but then basically so this would be the first thing. The second thing is that it actually, that this lambda I has to be invertible, so it cannot be a non-invertible symmetric, and that the representation is either the identity or the alternating one. Yeah? And then there is sort of this one n equals 4 I mean counter example. And then with this specific example of the n equals 2, I mean why we do this is that there we have a guarantee that we have exactly marginal deformations in the twisted sector. I mean, that is actually not so easy to maybe show. I mean, that if you just take, say, some bosonic model or so. I mean, so, and then we show that indeed, I mean, basically, generically, these things exist, but they're all basically, they're all invertible. Which, again, I guess, as so I said, I think this is maybe not so surprising. I mean, but maybe a little disappointing, but maybe at the end, maybe good. I mean, because it's still probably a challenge, I think, to think if you have this deformation away from the orbifold point, it will break, say, this enhanced symmetry, it will change the spectrum. So it might go, and if it's possible, I mean, if you imagine that such a deformation would take you to a point which actually is described by semi-classical gravity, then it would be quite a challenge, I think, to think about what non-invertible defect lines actually would mean, I mean, from the gravity point of view. And I'm sorry that I guess this went maybe a little big, but I guess the paper is coming out, I think, tonight, so there's more details. And as I said, there is sort of like a whole, I mean, this is very pedestrian, like using this like projectors and the folding trick, etc. But then we have a whole sort of other part, which is sort of redoing these arguments, basically using the language of category theory or so. which, I mean, you might have guessed by my presentation wasn't really written by me. But I think it's quite instructive. I mean, that there are sort of two ways of doing this thing, and that's why I think we decided to do this, how we put this out. Okay, so thank you for your patience.
Any more questions?
Some people discussed recently the TT bar deformation. That
Yeah.
probably preserves all the TDS.
Yeah, I mean, so basically, I guess there is sort of, I think in this, you have sort of
Of the
different
free
choices
orbifold,
there.
TT
I
bar
mean,
of the free orbifold.
yeah, because, I mean, even there you have choices. I mean, because basically what you have, I mean, at the orbifold point, I mean, you have basically n copies of the stress tensor. So you could say, take TT bar, TI bar, and then symmetrize, or you could take the sum of TI.
I meant
And
the
the sum
latter.
of TI
I meant
bar.
the latter.
Yeah.
That's,
I mean, I would say that this is sort of like, I mean, this is I guess I mean, this has dimension 4, so it's not really, I mean, basically, I should say, I think a lot of this would actually also work, I mean, for renormalization group. I mean, which would be, I mean, it's not a TT bar, but it would be like basically looking at, I mean, RG flows, I mean, where again, I think there are, in this, say, at least in this n equals 2, there would probably be plenty of things you could construct
TT
there.
bar is also an RG flow. What's the problem?
Yeah,
I
well,
didn't get it.
okay, I mean, it's an RG flow up, yes, yeah.
Yeah,
But it's in the untwisted, yeah, so I would actually, I mean, I would say that this is an basically, I mean, our analysis doesn't apply because I would think it's like a deformation in the untwisted sector. So, but I guess if you take that, so which one, you did the sum of TI times the
both
sum of
appear in
TI?
the literature.
Yeah, no, I know.
Buika's papers and the other,
Yeah.
in Kutaso's paper, both are interesting.
Yeah. I mean, I hadn't really thought about, but say if I would take the sum of TI bar, it's sort of more like that. Basically, there is sort of a TT bar deformation in every factor of the seed theory, and I'm not 100% sure what's going on in the other one. That's probably more interesting. But yeah, I mean, but I should say that I think I mean. I mean, in the untwisted, I mean, it's untwisted, and we would the line. Yeah, I mean, it would sort of naturally preserve.
Yeah,
Yes,
preserve
yeah,
it,
exactly,
yeah.
yeah. So I mean, we haven't thought about it, but I guess that's. I mean, I don't know. Do you remember what is the? I mean, sort of. What is the endpoint of that? I mean, or what is the thing it lends to? I mean.
Yeah, it's supposed to disbuilding the Mezei proposal to bring in the boundary.
Okay.
It's supposed to be like ADS becomes like a finite cavity.
Right. I mean, but then you would say, okay, like if all these non-invertible symmetries are still there, I mean, what would they mean? I mean, that would be certainly very interesting. So I don't know. I don't know whether people have thought about it. I mean, we are.
I guess you'd bring supersymmetry probably, right?
Well, I mean, some of this, I mean, the supersymmetry here was really just, I mean, for us, I mean, I think these arguments work, I mean, in some sense, because it's topological, I mean, they don't really rely on supersymmetry, I think.
Yeah, actually, maybe that's a question. Why was supersymmetry?
No, well, basically, for us, it was just that then we had a guarantee that we had basically exactly marginal operators in the twisted sector. I mean, the other thing where you kind of have guaranteed, you know, like marginal deformations would be like U1 current deformations, but those I think I would really, at this point, only know really how to construct in the untwisted sector. So, and that wouldn't necessarily like move you away, sort of, in that sense, from the orbital.
But those are probably their SN invariant current.
Yeah,
deformations in
exactly.
general, right?
Yeah, but I mean, that would be sort of like a deformation basically of the, I would think of it like a deformation of the seed. I mean, say that you take a T4 and you take it to a different point in this moduli space. I mean, that, you know, that would probably be less interesting.
Other questions? Okay, then let's thank Eric again.